Hi, everyone. Thank you for joining our talk. It's called Explaining Explain. It's an introduction to PostgreSQL explain plans. And I hope that it will be a very useful talk for you. I found this feature of Postgres to be very useful for DBAs, developers, sysadmins, basically anyone who uses Postgres as a database. Just to get started, a little bit about myself. I work at at EDB as a support engineer since 2015. Does that sound? That's from outside. It's not from my microphone, right? Okay. Okay. I just want to make sure. Yeah, before I worked at EDB, I was a DBA and a web developer, and I've been using Postgres since version 7.4. So basically, what I wanted to share about this feature is basically comes out of my experience as a support engineer. And the most common question that I get from our customers is, why is my query slow? And the answer to that question is actually very difficult to pinpoint. It could be a lot of factors. It could be a slow network. It could be high concurrency on your operating system. It could be bad kernel tuning. It could also be just a lot of resource contention, like your disk and stuff like that. So the way to figure out whether it's the database or whether Postgres is doing something that makes the query slow, we use this feature called explain. And this has proven to be a very powerful tool, and it gives you a live look at what's going on in the database. So during this talk, we're going to cover just quickly what is explain, what does it do, how does it work, and how do I get explain output, and how do I interpret it? So, and then finally, we're going to go over some non-trivial, real-world examples of how explain can help you as you use Postgres. So to start off, so what does explain do? Explain is what Postgres plans. It tells you what Postgres plans to do for a query. So when you type explain and then the query, it will print out a query plan, all the things that it chooses to do in the process before it gives you the results. Now, it can also tell you what Postgres did for a query, which is what explain analyze does. So if you type explain analyze and in your query, you're going to get some statistics about what the query executor encountered during the execution of that query. Okay. Now, that's pretty cool. Now, what doesn't explain do? So I think before we kind of get carried away with just like, oh wow, this is going to improve my my experience as a user, we need to know what explain doesn't do. And what explain doesn't do is it won't explain why a query planner made a choice. It only tells you what choice the query planner made. It doesn't tell you why it chose that. It also won't tell you about a query's performance being affected by another session. So if you got some locking going on through another session, it won't say, hey, this other query is blocking you and causing your query to be slow. It also won't tell you about stuff that's happening outside the database. Like, let's say your operating system is doing some kind of flush of the cache or doing an antivirus scan or something like that, and therefore the disks are slow. It won't tell you stuff like that, like, hey, your operating system is causing it to be slow. It also won't tell you anything about external environments, like, hey, your network's slow, there's a lot of network latency. So these are the things that explain won't do. Okay. Now, just going back to the top, the top point, explain has something to do with the query planner. Now, if just kind of real quick give you an overview of how Postgres executes a query. When you type in the query and you press enter, that query gets sent to the postmaster, and it decides. It runs a query planner and generates a query plan for you. Now, how does that query planner work? The way that query planning works is cost-based. So based on some configurations in your conf file, it will calculate the cost of certain actions, like a sequential scan or a HashJoin or whatnot. And that cost that's calculated gets taken into account for those decisions that it needs to make. It also uses statistics that's stored, and those statistics are stored in the PG statistic catalog. It's not human readable, so don't look there if you're kind of interested in what kind of statistics they are. If you do want to know, looking at PG stats, which is kind of a processed version of PG statistics, and there's not a lot of documentation on how to interpret it, so I won't get into those details here. Those statistics are refreshed every time you call analyze. So I don't want you to get confused between explain analyze. Explain analyze is a kind of a two-word keyword that tells explain to the query planner to print out all those plans and stuff like that. Analyze by itself, and sometimes used with vacuum, will scan a table, collect statistics about the values within those tables and columns, and it will store that stuff in PG statistics. And once again, this is all done by configuration. So I'm going to give you a quick overview. Those configurables are things that say enable, that begin with enable, and then also end with the word, either begin with enable or end with the word cost. Okay. So here's actually the list of all the configurables involving the query planner in the PostgreSQL.conf file. You can actually generate a listing of these configurables through this query right here on the screen. Now, there's a lot of stuff here, so it can be kind of intimidating to look at. For the most part, unless you're getting really deep into the, really deep into some kind of query tuning issue, you won't need to tune all of these. The ones that you're most likely going to touch are going to be these two over here, called sequential page cost and random page cost. Okay, so let's actually now go into some examples. Okay, so what does explain do? Like how does it work? So I'm going to just basically use PG bench with no extra flags. It's just basically load up a PG bench, and then if you want to follow along with these slides later on, you can just quickly spin up a PG bench instance. So explain, like I said, it tells you what Postgres plans to do to get that data to you. And when I type explain select star from PG bench accounts, and then join PG bench branches, and get only the rows where AID is less than 100,000. It's going to print out this query plan, right? And the query plan, you can see that it filters PG bench accounts at the bottom, and it gets only the rows that are AID less than 100,000. And then it does a sequential scan of PG bench branches, and then after those two scans are done, it joins it together using that equality operator. And then after that, the way that it does the join is by using a nested loop. Now, you might wonder, okay, so what are these costs? Like, is that how much time it takes, or is that like how many bytes or whatnot? The way that this works is by using, like I said, those parameters that were in the conf file. Okay, so we're gonna focus on this number 2890. Okay, how did the query planner calculate that? Okay, the way that it does that is through this formula. Okay, the cost is the number of blocks times the sequential page cost, which is found in your conf file, plus the number of records times the CPU tuple cost, which is also found in the conf file, plus records times the CPU filter cost, which is found in the conf file as well. So if you go through these, since you know that there's 100,000 records in the accounts file, accounts table, you can plug those in. The block size, which is typically 8 kilobytes on a standard OS, and then the number of blocks, which is the relation size divided by the block size, is 1640. So you plug that all in, and at the bottom you get 2890. So as you can see, these costs are basically tuned based on whatever you find in the conf file. If you change those numbers in the conf file, it basically tells Postgres, hey, it's more expensive or less expensive to grab a tuple from disk. And by doing that, you can actually affect the way that the query planner makes its choices. I'm going to get into that a little bit more later.
Okay. So now that was just the explain. That was just the plan. It didn't actually execute anything, so you don't know how long it actually takes to run it. Now, if you type explain analyze, the same query, you're going to get this result. It looks very similar with the one you saw earlier, but you're going to see now the second like kind of column-ish. It says actual time, actual rows, actual loops. So this is what the query executor encountered as it was processing this plan that it created. Okay, you'll see that the actual time to run it was 61 milliseconds, but the bulk of the time was, I think it was the sequential scan of the accounts table, which is 25.7 milliseconds. Okay, now the 56 milliseconds to do the nested loop is actually includes the time that it took to do the scan. So if you want to find out the actual times it takes to do the nested loop, you have to do subtraction. Okay. Now, okay, so I'm going to jump over. Now, okay, so sorry, I didn't advance these slides while I was explaining it. Now, the next thing you can do is in addition to using the word analyze, you can there's actually a bunch of other keywords that you can pass into explain. Those are found in the documentation. This one I'm going to share with you, which is called buffers. If you say explain buffers analyze, it will not only analyze it for you, give you all those statistics during the runtime. It will also share with you the memory usage of those nodes in the execution plan. Okay, so as you can see here, the output, the shared hit. So during the sequential scan of pgbench accounts, it hit 2 buffers, and then it read 1638 buffers. Okay, so what that means is within the cache, the shared buffers cache, it found two buffers. I believe those are blocks. So it found 2, and then it had to read 1638 buffers from disk. So this was a read-heavy operation. It pulled data from disk, put it into memory for you. Okay, if you run this query several times, you might actually be able to hit more buffers in the memory, and thereby get a lower execution time. But in this example here, we see the first pull pulls a lot of stuff off of disk. Okay, if you did like an update or an insert, you might see things like buffers that were dirty or buffers that were written, and that kind of that might be useful for you if you need to know those things. If you are seeing a lot of unexpected reading of the buffer off of disk, you might need to increase shared buffers because stuff is getting evicted from the cache, and every time you're trying to pull stuff in, you're pulling it and putting it into memory, and then the second time you pull it, you pull it from disk again, meaning that something between the two executions emptied the cache out. So maybe the shared buffers isn't big enough for you. Okay. The other keywords that you can pass into explain are things like timings of each node. You can output the stuff in YAML or JSON. You can actually get those examples out of the documentation as well. Okay. So just moving on. So as you can see, much of the query planning involves deciding what kinds of joins and scans should be performed. Right, so we've only seen the nested loop. I'm going to give you a few other examples. So we're just going to go in a little deeper here. So just to kind of create a little more, I guess, chaos or non-determinism, we're going to insert more data into the branches table. Okay, so I'm going to insert another 99,099 rows. And then I'm going to run the same query, explain analyze where AID is less than 100,000. And this is the output that I'm going to get. Okay, so now if you notice, at this point, it has decided that it's going to use a HashJoin instead of a nested loop. And this is because the branches table is now bigger, and a nested loop would not be efficient. Because previously, it was just 1 row in the branches table and 100,000 rows in the accounts table. So you just need to take one row in the branches table and then scan the 100,000 rows in the accounts table, and then there you got your join. But now you've got 100,000 rows and branches, 100,000 rows in accounts. You don't want to, for every row in branches, scan 100,000 times. That's going to take you too long. So what you want to do is you actually want to create a hash of one of the two tables, and then take the values that you want, and then compare it with the other table. Okay. Now, as I mentioned earlier about the cost, right? So here you can see the cost for the HashJoin is 48.38. Okay. Oh, by the way, sorry, I didn't get to mention this. The first number in the cost is the amount of well, first number in the cost and the first number in the actual time is the cost and time to the first tuple. Okay. And then the second number is the amount of cost or time to get the full set that returns to you. Okay, so here 1676 for the hash join is the setup cost. You gotta create the hash, you gotta parse the hash, and then by that time you get your first row, and you can print that up to the screen. Okay, so and then 4838 is the cost to get to the full set. Okay. So here the hash join costs 48.38, and the reason why that the query planner chose this join instead of the nested loop is because it's less expensive. Now I can actually force the query planner, hey, I don't want hash join. Okay, so if you say, hey query planner, I don't want you to do hash join, then it's got to think about, oh, what's next. Okay, so here's what I did. I say set enable hash join to off. And then now I run the same query again, and this time it says nested loop. And you can see here the cost here is 58.39. So now you can kind of see. So the query planner had this choice, nested loop versus hash join, and it said 53.89 versus 48.30. The hash join is definitely cheaper, so I'm going to go with that. So as you can see, the query planner is using that cost to pick the most optimal execution plan for you. Now again, if you change these enable values on or off, or if you change the cost values on or off, or up and down, you can actually trick the query planner, which you may or may not want to do that, depending on what kind of data you're working with. Question? Mm-hmm. So the question is, if you did set enable hash join to off, will it use this query plan for the remainder of, I guess, when it's up? So the set command for these enable and cost values are only for that session. Okay, so if you are going to just say, hey, I want hash join off, it won't affect anyone else. So they're going to continue being able to use hash join. But if you change it in your conf file and then you restart or reload the database, that's going to be applied globally. So you don't want to very quickly change those values in the conf file, because you can affect other queries or other users. Okay, so you want to just, for your purposes, you can actually just do it for your session, so that way you can kind of see what the query planner is doing. Okay. All right. Okay, so now going the other direction, I'm going to seek less rows. So I'm going to find all the values where AID is less than 100. So naturally, that's going to be what, like 99 values, right? Okay. Now, what happens if I do that? Now it chooses merge join. Okay, because it decides, hey, it costs only 16, or well, I didn't actually print out all the costs, but you can see. So there's the merge join, which is what we see here, where there's a nested loop, and then the hash join, which is what we saw earlier. Okay, so this is kind of a quick review of joins. Okay, so the nested loop is what we saw earlier. That, like I said, is you take the smaller set, and then you loop for each value in the smaller set. You loop through the bigger set. Okay. It could. My memory fails me. I think it might actually be the order that is listed in the query. So if you say select A join B versus B join A, the nested loop decision might be different. Okay. So note to myself, I should check that for my next talk. Merge join. So what that does is it will take two data sets that are sorted, and it will kind of like a zipper match them all together. So like, 1 and 1, okay, 2 and 3, no, 3 and 3, okay, and then join those together. Okay. Now this is good for large tables, right? But it will require that you sort it. So if you do have a large table and it's not sorted already, it's going to create extra processing for the query planner to do. Now HashJoin is the final join that we have here. Now what that does is for a value that you're looking for, you want to build a hash of, for a table you want to build a hash of all the values, and basically by nature that's going to be sorted. You can take your equality search value, and you're going to go down that hash and find the right entry to do the join with. Okay, so this is actually going to be even more startup costs because you got to do sorting and you got to do the hashing. But once you do the execution of it, it's actually very quick because you already you're able to find the equality pretty quickly. So this is only valid for equality operators. So you cannot do like hash join with a less than or a greater than. Okay. So these are the three loops. They all have their own purposes. So we're going to move on now. So let's say so now what I'm going to do is I'm going to create a little bit more, I guess, unpredictability. So in the accounts table, once you load up pgbench, all 100,000 rows are going to have distinct AIDs, but the BID is going to be 1. Okay, so it's going to be if you do where BID equals 1, you can actually pretty quickly get to that. You're gonna get all the values starting from the first row that you hit. Okay, but here what I'm going to do is I'm going to set BID equals AID. Okay, and the reason for that is because AID is indexed, but BID is not. Okay, so we're gonna explore indexes here. So so let's say I update all the BIDs, and now they're all distinct values. Okay, and I do explain, analyze, select star from pgbench accounts where BID equals 1. What you're going to get is the sequential scan, and you're going to filter out 99,999 rows because only one row has BID equals 1. And that's going to take 45.1 milliseconds, which isn't that long in real world human time, but in database and software time, that's actually quite a long time. And that's usually pretty unacceptable in a large production environment. So what we do is we create indexes. And by doing that, we actually map out all the values of BID, and then we actually tell where in the memory or where on disk the actual row is. So it's kind of like a shortcut to get to the rows that we want. Okay, so I create the index, and then I run the same query again, and now I'm down to less than a millisecond, about a tenth of a millisecond. So as you can see, having an index helps a lot. Okay. Okay. So as I mentioned earlier, so indexes help you get your information faster. Now the thing is, the way that the index works, like I said, when you say I want a value where BID equals 1, it looks at the index, it scans through it, finds the row that BID equals 1, and it says, oh, here's the address to the disk, and I'm going to go to the disk and pull it out. Okay, so you're still pulling stuff off of the disk or out of your cache, and then returning it to the user. Now, as a developer, that can be improved. Okay, the way that you can improve that is by knowing that there is an even faster scan in Postgres. which is the index-only scan. Now, you see the bottom query on the screen here. When I do select AID from, okay, so when I select AID from PGP accounts where AID is less than 1,000, the execution time drops from 0.8 milliseconds to 0.2 milliseconds. Now, why is that? Because when I had my account ID AID scanned, it scans the AID primary key index, grabs 1,000 rows from the index, then grabs 1,000 rows from the disk, and then returns it to the user. Okay, because I need star. I need everything for that row. Now, that can be sloppy, because let's say you want only the AIDs, because I just need an AID to do some kind of other lookup for another query. If I select only AID, then I'm gonna look in my index for all the rows in the index that are less than 1,000, and then I don't need to go to the disk anymore because the query only asks for AID. So then I send that right away, and by doing that, I save 0.6 of a millisecond. Okay, so I guess the point of all this is to encourage you, if you're a developer or if you are responsible for writing reports, you do want to be very specific about what columns you return and what indexes you create. So here I have an index on AID. I just want AID. I can actually do a quick index scan and send that to the client. Now, as I mentioned earlier, again, those costs that you can tune. Random page cost is what affects the choice of an index scan, because it's the cost of fetching a random block off of a disk. So if you have an SSD, you can actually tune that way low because it doesn't cost much to pull random blocks off of an SSD. But if you have like a old spindle drive, you will have to tune that up, and you want to keep that higher. And depending on the RPMs of that disk, you can tune it down or up and down. Okay. So this is just to illustrate what happens when the cost gets too high. When the cost gets too high because of having a really big index or some other reason, you can the query planner will eventually choose, hey, I'm going to just get the sequential scan instead of the index scan. So I'm explaining this to you because a lot of our customers have come to us and say, hey, I have an index, but the query planner is not using it, right? And when we look at it closely, we realize, hey, the query planner isn't choosing that index because you're trying to get too much data out of it. Okay, so like for example, if you have 10,000 rows and you want AID is less than 10,000, you're gonna eventually get all the data off that table. So you might as well just do a sequential scan rather than doing an index scan and then a random page pull, right? So just knowing the size of your tables and knowing what your query is trying to do will help you understand why the query planner made a certain choice. Okay, so just a summary over all the scan types we went. There are sequential scans. You scan the whole table. You're going to choose it because you're going to retrieve most of the table or not. Index scan, you scan all the index and then look up the rows on the disk. Causes a random seek, so you want to tune. You want to be aware of that. Index only scans only the rows in the index and doesn't touch the disk. And then finally, there's a scan that we didn't go through, which is the bitmap heap scan. So what this does is it scans the index, and then it builds a bitmap of all the pages that it needs to pull. So rather than going index, here's the index, pull the disk, index, pull a disk, index, pull a disk. You're gonna build a bitmap and like, hey, 5 of these 10 rows come from this part of the disk, and then 2 of these rows come from this part of the disk. So it actually makes it more efficient that way. Okay. All right. So this is the fun part, explaining the unexpected. Okay. So some of the real world non-trivial things that explain can do. Now, so one reason why you might be getting a slow query is probably because you have some bad statistics. So in this example, what I show you is when I do explain analyze on a query, I get an estimated 35,360 rows. But when I actually run it, I'm only getting 170. Why? What happened? It's because remember what I said. All the query plans are generated based on statistics stored in the PG statistics catalog. Okay, so whatever's stored in there right now is not very accurate because in reality there's only 170 rows. So what you do is you call the analyze command, and then you run it again, and then now you get something a little more accurate. Right, 153 estimated versus and it's a lot closer to the actual number of rows. Now, again, this is a estimation. It doesn't scan. I'm not gonna say anything wrong, but so, but what's stored in statistics is generally an estimation because it cannot. If you have a really large table, like billions of rows, you cannot store everything in there into statistics. Otherwise, you might as well just have that table all over again, right? So it does some heuristics or like histograms based on what its calculations, stores that in statistics. Okay, so if you encounter this kind of situation where your statistics are way off, that's usually a clue that you have not vacuumed and you have your auto vacuum is poorly tuned or is not running at all. So you do want to make sure that you set auto vacuum properly. Now, that's beyond the scope of this talk. So, please do Google, how do I tune auto vacuum, and that will definitely help you a lot. Now, there are some times where you're going to see that the query planner didn't choose an index that you expected it to use, and this is sometimes it's caused by rows that are or columns that are correlated, but the database doesn't know about it. Okay. So like, for example, if you have a table that says cities and then another table that has states and you want to do some kind of join, Postgres doesn't know that a city is inside of a state. And it wouldn't know to take advantage of some kind of index relating the two. Now, if you need to create that correlation, Postgres has this feature called create statistics, which creates an additional set of statistics for the query planner to use. That is, again, outside of the scope of this talk, but please bear in mind that this exists, and if you do need to make any kind of correlations in your queries, this would be the way to do it. Another real-world example of queries being slow and being able to help you with that is insufficient memory allocation. Now, in this top example right here, you see that it took about 2.3 seconds to run this query. And the reason for that, if you look, it says external merge disk, 2,664 kilobytes, which is 2 megabytes. So basically, it created a 2 megabyte file on disk to do some sorting for you. So sorting on disk is very slow, and that usually indicates that you have not allocated your workmem properly. So workmem is a configurable that allows you to create space in memory to do joins and sorts and stuff like that. Okay, so as you can see, once I've increased my workmem and I run the exact same query again, it does that sorting in memory, and the query is a lot faster. It has dropped down to 2.1 milliseconds, 2.1 seconds. Okay. Like the enable HashJoin example I showed earlier, the workmem is also per session. If you change it in your PostgreSQL.conf, it could be dangerous. If you set it too high, you could actually cause out-of-memory errors. So just keep that in mind. One more example is index definition mismatch. So here's my example of an index I created, and I am indexing the AID column and a substring of the filler column. I want the first character. Okay. Now, if you look at the following two queries where I actually attempt to use that index, the query planner doesn't use it. And the reason for that is because I have defined the index a certain way, and I'm calling, I'm doing an operation that is not similar to how the index is defined. So if you see the two wrong examples, and then the final example where I call it the exact same way is using the index scan. So this is useful because if you are wondering why your query is slow, explain analyze, you can see, hey, it didn't use this index. It used a sequential scan instead, or like a bitmap scan instead of a index scan. Now the reason again is because maybe the query itself wasn't written the way that would tell the query planner, hey, I want to use this index. Okay. Another example here using like JSON values. Okay, so if you want to create multiple indexes based on some way that you're going to call a column, that's fine. But bear in mind that you could incur a higher write cost. Every time you insert, every time you update, you got to update that index, so it actually reduces your performance in the long run. Okay. A few other situations, prepared statements. So if we have seen situations where if you do a prepared statement and you call execute on that prepared statement many times, you could end up with decreasing performance. Because the way that it works is the first 5 executions of a prepared statement will use a custom plan. It will take the value that you pass into it and then generate a new plan and then run against that value. Now, again, planning takes time, right? And if you're going to call multiple times, you don't want to incur that cost of planning. So what Postgres does is creates a generic plan on the sixth try, and then uses that one. But that generic plan isn't always the most optimal performance. Now, in version 12 and later, you can actually adjust the plan cache mode, and you can tell it, hey, always use a custom plan. Hey, I don't mind the cost of query planning, so always generate a custom plan for me because that's going to be a lot more performant. Join order can affect whether you choose index or not. And then the just-in-time compilation feature, which is very useful for ETL, has bitten a lot of our customers because it's doing this additional work that is not necessary for their application. So you might want to turn off just-in-time, the JIT in your PostgreSQL.conf, and then see if that improves your performance. From collapse limit, join collapse limit, that also affects your performance. If you have, let's say the from collapse limit is default 8. So if you have select star from table 1, 2, 3, 4, 5, 6, 7, 8, the query planner will take those 8 tables, create a plan, and then execute it. But if you have more than 8 tables, the 9th table, it actually just omits it and then tries its best to guess. And that guess is sometimes not very efficient. And same thing for join. So table 1, join, table 2, join, table 3. Those kind of, if you join too many tables together, the query planner will try to collapse it all and then do some estimates. And you end up with a really fudged up query plan. The final one I want to share with you is ORMs. So if you are using Django, if you're using, I think, I forget the other frameworks, but some applications will use an ORM. And sometimes those ORM, the way that it constructs the query is very opaque, and you do not know what it's doing under the hood. And in this example, this was one of our customers. They had a a simple update statement, which they said, hey, this is taking like 40 milliseconds, and it's, we do it 100 times. It's taking 4 sec. They do it like 1,000 times, and it takes over a minute to do all the updates on all the rows. But then when they run the updates manually, it only takes 0.25 seconds, 0.25 milliseconds, which is really fast. So it's really puzzling why this update is taking. And the reason we were able to figure out what the problem was, and we found out that it was taking 40 milliseconds, and the reason for it, and the explain analyze output showed us, is that there was a data type mismatch. So the table was defined with numeric values, but then when we ran explain analyze on it, you found out that the ORM was converting it from casting it to double precision. And when it was casted to double precision, it could not use the index, right? Let's see, this update uses an index, but the other ones were using a sequential scan. Okay, now how do we do that, right? Because if they're running the application that's doing thousands of queries, a second, they can't step in and do explain analyze. Now the way that we do that is by this feature, this module that we have is called AutoExplain. Now this is an extension of Postgres, so you have to load it into your database. Now what it does is it prints explain and explain analyze to your log file. So if you turn it on and then just run your script or whatnot, it'll print out all the explain analyze output based on the settings that you set. And it can even do things like explain analyze on the nested statements, or if you have a function that calls a select, it will print the explain analyze of that select within the function, which you can't do with just regular explain by hand. So this is very, very useful. In addition to this customer example that we had earlier, I recently had a customer who was having some row level data security issues, and we found out that they had a function that was trying to set an environment variable, but that environment variable wasn't being set properly. So they were using old values of that environment variable, and that's why they were seeing stuff. Their clients were seeing stuff that they shouldn't have been seeing. So AutoExplain actually allows you to have that kind of ability to see deeply. I'm sorry, question? Can you turn it on and will it affect the Yes, it does. It creates a lot of additional I/O. So you only want to turn it on when you're actually looking for an active problem. So yeah, so you can turn it on per session with load AutoExplain in your PHQL session, or I guess in your application, or you can turn it on at a conf level, which would be system wide. Which I mean, if you have to, you should. But if you can turn it off to save yourself from performance, that's better. Okay. I'm sorry? Right. Yeah, so the best way to do is find out the problematic query and then turn it on and then get it to print out the explain analyze output and then turn it off. Okay? All right. So that was it for my talk. Thank you guys for attending. I hope that it was useful.